In 1961, the Soviet Union detonated the RDS-220, better known as the Tsar Bomba, releasing a staggering 50 megatons of explosive energy. To quantify exactly what 50 megatons means, that blast was roughly 3,800 times more powerful than the atomic bomb dropped on Hiroshima. This chart puts that yield into perspective. The total explosives used throughout all of World War II equals about 3 megatons. The largest United States nuclear test, Castle Bravo, reached 15 megatons. The Tsar Bomba dwarfed them both at 50. Political history often frames this detonation as a display of brute force, meant by Nikita Khrushchev to intimidate Western leaders. The internal design reveals a more precise reality. The Tsar Bomba represents the absolute physical boundary of atmospheric weapon design. Building a weapon of this size requires overcoming a central engineering bottleneck, the physical impossibility of maintaining symmetrical compression at an ultra-high yield. To solve this, Soviet engineers had to abandon standard geometries and invent an entirely new three-stage architecture driven by two perfectly synchronized primary triggers. Deconstructing the mechanics of the Tsar Bomba reveals exactly how the largest weapon in human history was built and exposes the strict mathematical laws that prove why a bomb of this scale should never be built again. To understand why the 50 megaton yield required an entirely new architecture, we first need to look at how a standard hydrogen bomb actually operates. Most modern thermonuclear weapons rely on a two-stage process. The entire chain reaction begins with the first stage, known as the primary trigger. In a standard two-stage weapon, the primary atomic trigger generates a massive burst of X-ray radiation. These X-rays travel down the radiation channel, applying immense, perfectly even pressure around the secondary fusion capsule. Under this symmetrical compression, the isotopes fuse, releasing vastly more energy. The problem with this standard geometry is that it does not scale infinitely. Once you attempt to build a weapon past the 15 to 20 megaton range, the radiation channel becomes too long to compress the secondary stage evenly. Hitting a 100 megaton target meant Soviet engineers had maxed out the physics of a two-stage weapon. They had to invent a third stage. Looking at this expanded diagram, we see the structural shift of the Tsar Bomba. The engineers added a massive tertiary fusion core directly in the center, and rather than a single primary trigger, they used two. This layout introduced a highly complex engineering challenge, compressing a central tertiary core of that mass evenly enough to actually ignite it. A single primary trigger fails completely at this scale. Radiation striking the massive tertiary stage asymmetrically would push the core off-center, destroying the device. The architectural solution was placing a primary trigger on both sides, but having dual primary triggers meant they absolutely had to be synchronized perfectly. Both fission triggers had to detonate near simultaneously, requiring precision down to the microsecond. If one primary detonated even a fraction of a millisecond earlier than the other, the X-ray pressure inside the radiation channel would warp. This results in what weapons engineers call a fizzle. The intense, uneven pressure violently blows the bomb itself apart before the tertiary fusion sequence can successfully propagate. The chief physicist on the project, Andrei Sakharov, and his team managed to crack this precise timing matrix. Achieving this level of synchronized compression without the aid of modern digital modeling was a significant feat of analog engineering. Solving this synchronization barrier allowed the team to finalize the mechanical design and achieve the target ultra-high megaton yield. While the historical record shows the Tsar Bomba detonating with a 50 megaton yield, this completed architecture was actually designed to release a full 100 megatons. This split-screen diagram highlights how they plan to reach that number. The original 100 megaton design called for a tamper, the outer casing surrounding the fusion stages, made of uranium-238. This material enables a fission-fusion-fission reaction. As the fusion stages burn, they release a flood of high-energy neutrons that strike the uranium tamper. The uranium-238 undergoes fast fission when struck, generating a massive secondary explosion that would double the total blast yield. But this specific fast fission reaction has a catastrophic drawback. It creates an immense volume of globally lethal radioactive fallout. Sakharov intervened late in the design process. His calculations showed that testing the full 100 megaton weapon would directly cause hundreds of thousands of premature deaths worldwide from radiation exposure. At the very last minute, the design team replaced the highly reactive uranium-238 casing with biologically inert lead. The lead tamper is dense enough to contain the internal radiation pressure required for the fusion stages to ignite, but it does not undergo fission itself. This substitution choked off the final fission stage entirely, intentionally capping the explosive yield at 50 megatons. By cutting its own explosive power in half, the Tsar Bomba became, relative to its size, the cleanest nuclear weapon ever detonated. During the test, the bomb was dropped from 4,000 meters and detonated mid-air to further minimize radioactive dirt being kicked up from the ground. As this map illustrates, the initial ground-level destruction was absolute. Every tree, building, and rock within a 35-kilometer radius was leveled. But this graph visualizes the fundamental physical limitation the detonation exposed. Explosive blast damage scales by the cubic root of the yield, not linearly. The mathematical reality is that a 100 megaton bomb releases exactly 10 times more energy than a 10 megaton bomb. Yet, because the atmosphere is flat relative to the blast, that massive 10x increase in energy only doubles the two-dimensional damage area on the ground. The atmosphere simply cannot contain that much force. The excess energy faces less resistance pushing vertically than it does pushing outward, so it blows straight up into the vacuum of space. The proof of this vertical displacement was the mushroom cloud. It soared 64 kilometers high, piercing the stratosphere and expanding deep into the mesosphere. This map comparison demonstrates the glaring inefficiency of megatonnage. Mathematically, dropping 5 5-megaton weapons spreads the explosive force out, causing significantly more area damage than dropping a single 150-megaton bomb. Nuclear strategy quickly shifted to match the math. Militaries focused on smaller warheads that cover more surface area and are vastly easier to load onto ballistic missiles than a bulky 25-ton bomb. The Tsar Bomba proved that high-precision synchronization could overcome the scaling bottleneck. Ultimately, it also proved the physical limits of atmospheric destruction, closing the era of the ultra-large bomb forever.